And this is my first video on a multiple part series about computer architecture. So we're going to start with the very basics in this video today, and I'm going to do each video in one part, no cuts. So just to give you a brief background of why I'm making this series is because I'm really passionate about electronics and computer architecture in general. So here is a computer I'm currently working on. It's a 16-bit processor, and it's a single bus, sort of like, I think it's based on the SAP1 architecture. And this computer involves a lot of addressing modes, lots of instructions, a lot of RAM, Ben Eater's video card, which I upgraded to have its own VRAM, and I also made the pixel density multiplied by 2, and I add a comparator board alongside with an ALU that has a lot of operations. Also, when I was in grade 12, I created this processor right here. So the processor you saw before and this one have a lot of similarities, but I added much more features in the other one. I also created 3 other computers, one in grade 9, in between grade 9 and 10, one in grade 11, and then the one you just saw, which I built in grade 12. So let's just begin. So we're just going to start with the very basics of digital electronics. Okay, the first thing we need to understand is binary. So you know your regular numbers. Let's say we know 13, we know the number 20, we know the number 5,326,512, for example. And we know that there's a tens place here and there's a ones place here. We know that there's a tens place here, ones place here. We know that there's a millions, the 100,000s, the 10,000s, the 1,000s, the hundreds, the tens, and the ones. Okay, that's cool. But what if we only had 2 digits? We only had 2 digits. So in a computer, we could only represent a 1 or a 0. And pretend we have a wire right here. So we have a wire, just a regular piece of metal. Okay, and we could put in a high voltage. So we could have in a high voltage, pretend it's 5 volts. And we could have the low voltage, pretend it's a 0 volts. And what we say is that the 5 volts is given the number 1. Okay? 0 volts is given the number 0. This is what we have decided. Okay, that's cool. How do we even represent a number? I'm telling you right now, binary is easier than decimal numbers that I just showed you with the 13 and the 20 and the 5 million. Binary is easier. Let me tell you something. 2 to the power of 0 is equal to 1. 10 to the power of 0 is equal to 1. So in binary, this is our first digit. The first digit place is something, the base raised to the power. So we're in binary, so we have 2 digits, so we have 2 to the power of 0, we get 1. And remember, in decimal, we have base 10, so we do the same thing. 10 to the power of 0, we have 1. So in binary, we have the ones place here, and we also have the ones place. Okay, let's go to the next place value. So in binary, we have 2 to the power 1, that's the next place value. This is just 2. Okay, and then in decimal, we have 10 to the power 1. That's the next place value, which is 10. Okay, let's go to the next place value. In binary, we have 2 numbers, so we keep the base, and we go to the power 2, and that's 4. In decimal, we have 10 to the power 2, and it's 100. Now you can see the pattern here. This is the ones place, the tens place, the hundreds place. It'll go on forever until the billions and trillions and quadrillions and quintillions, and you know, it just could keep going on forever. You could just keep giving it names. Now in binary, we have the ones place, the twos place, the fours place. What comes after? The eights place. What comes after? 16, 32, 64, 128, 512, 1024, 2048. Okay, so now we have a way to represent numbers with only 2 digits. Okay, that's cool. Now what if I have a line right here, which is a wire, just a wire, then we have another wire, then we have another wire, then we have another wire. So we have 4 wires. And I, the designer of these wires, just put meaning to what each wire means. So I'm saying, okay, this wire, I'm going to let it represent 2 to the power of 0. Then I'm going to say this wire represents 2 to the power of 1. Then I'm going to say this wire represents 2 to the power of 2. Then I'm going to say this wire represents 2 to the power of 3. Okay? Now, we could represent numbers using wires. Okay? This is what you call a bus. This is a bus, just a set of wires. Nothing more complicated than that. And each wire could have a 0 or a 1. So you could put voltage on it, or you could have no voltage on it. Remember, I said the 5 volt is equal to a 1, and the 0 volt is equal to a 0 in binary. This is what we have just come up with. We decided that 5 volts is a 1, 0 volts is a 0. This is what collectively, when they're first designing, they're like, okay, do that. You can make it whatever you want. But with the logic I'm going to be explaining, we're going to go with the convention that 5 volts is a 1 and 0 volts is a 0. Okay, now we go to the analogy of water. Okay, so pretend you have a river. Okay, so you have a river here. Pretend there's water flowing. Okay, and pretend you put like a little turbine here. Pretend this is a turbine. And as the water is flowing in one direction, it has a current. It's flowing in this way. And the turbine is spinning, right? So you could think of, pretend this is a wire, and instead of water we have electrons, and instead of something spinning we have a load, maybe like a light, maybe like a motor. So this shows that water and electricity, you could think of them in the same way. Okay, that's cool. Now let me tell you, pretend we have a pipe of water. Okay, then we have a valve here. So I'm just going to draw a valve like this, and with a little thing that you could turn. So this is just a pipe. But what if I add another valve right here? Okay. So pretend there's just water coming in here, flowing through. There's a valve. So someone's going to have to turn it, okay, to let the valve open up and let some more current go through. Okay. And what if you have another valve here? That means someone else has to come and turn it. Then, at that point, then water could fully flow through. Okay, so let's call this tap A, tap B. Okay, and we could make a little truth table. What I want to say is I want to know the logic of how do I get water on the other side. So we have A, we have B. Okay, now we could say that when the tap is closed, meaning that no water is going through, when the tap is closed, I'm going to represent that with a 0. So pretend tap 0 is closed, tap B is closed. What does our logic tell us? If this is closed and this is closed, the water's coming in, it can't even pass this first tap. So obviously there's not going to be any water there. So we get a 0. And I'm going to label this as output X. Okay? Okay, what if I have the first tap on, and we're going to represent when the tap is open, which means that water could go through. We put a 1 there. Okay, but let's say tap B is still closed. What does the logic tell us? This one is open, so water could go through here, but the second it hits this, it can't get through X, so we put a 0 there. No water flows. Okay, let's flip the roles. Let's say A is first blocking water, but B lets water go through. Wait, but no water could even get through A at first, so how could it even get to B in the second place? And we said that this tap was open, letting water flow, but there's no water originally coming. So we get another 0. Okay, the only way water could get through here is if A is a 1, B is a 1, then we could get water flowing through. Okay, so if you want to say this in a statement in English, you say A and, literally the word and, B need to be on, then X equals 1. This is logic. So we give it a symbol. This type of logic, we give it a symbol. We give it a piece of toast. It looks like a toast piece. So it has the output X. You could have the valve, like this is like someone turning the valve. So we have the A, and we have the B valve. Okay, so if there's a 1 on this on the A signal, that means someone turned this tap on. And if there's a 0 on this valve, that means someone closed it off. And this could be either for A and B. Okay, so I just introduced you to the AND gate. Now, you could forget the water example now. Now let's think of electricity. Okay, so I taught you about the AND gate. Next, we're going to learn about the next gate. Okay, we're going to learn about another gate. So let's say we have a tap here. So I just draw the tap like this. Water is coming in, but I have another tap here. Water could come into here. And then I have the two taps meet up. The two tap meets up and we get the output. Okay, let's think about this logically. Pretend there's water going in here, water going in here. Okay, and we have B here, we have A here. So I'm just labeling this A tap and the B tap. Now what does the logic tell me for this one? Okay, let's do this. Let's draw the truth table like before. We have the A tap, the B tap. We know that these are all the combinations of the taps. These are all the combinations. They could both be off. One of them could be on, or both of them could be on. Okay, if we have this structure, this is pretty trivial because look, if no taps are open, we get the 0. If one of them, we're still getting a flow of water. If one of the taps at least are on, then at least this one could go on. Same thing with the other one. At least one flow. What if they're both on? And then we still get the 1. So this is called, in English language, we say A or B, then X equals 1. Okay? We can see that. This is OR. A or B could be on, then we get the output as on. So this is called the OR gate. Okay, this is pretty cool. Now I'm going to just throw the water analogy out the window, and I'm going to introduce you to the simplest of gates. This is a symbol. We have the one input A, one output X. And I'll just tell you the truth table, and it's really simple. So we have the input, these are the only combinations. We could have a 0 or we could have a 1. And on the output X, pretend there's no water even going in through here. What this one does is it just magically creates water here for you. And if there is water here flowing through, it just magically deletes the water. So we could see that they're the opposite of each other. This is called the NOT gate, because the input A will not be X. It will never be whatever X is. They're opposite of each other. This is the NOT gate. Okay, now let's do something really weird. Let's take an AND gate. Remember, don't think of the truth table. Think of logically. Think of it as AND. Logically AND. A and B need to be on, then the output will be on. Okay, but what if a NOT gate right there? Okay, let's first draw the truth table for the AND gate. So you have A, B, X. I'm just going to quickly go through this. We have this. Okay, so this whole truth table, we're going to label this point as X. This is what point X is representing. Okay, but let's label this point as Y. Now let's make another entry. And you don't even need to think about anything, because whatever X is going to be, it's going to be the opposite. So we put a 1, a 1, a 1, and a 0 there. Okay, this, we give it its own symbol. We just put the regular AND gate with a circle. Okay, it still has 2 inputs, 1 output. And what do we call this one? We call this one NOT AND, or for short, we say NAND. Okay, but let me tell you something even better. Forget this truth table. Okay? Actually, let me just draw it quickly one more time. I shouldn't have erased it, but good practice. X, and we have 0, 0, 0, 1, 1, 0, 1, 1. Okay, and then we have the 0, 0, 1, 1, 1, 1, 0. Okay, wait. Let's try to put this logic in English. We see that the outputs are going to be 1, let's try to find, let's forget the x, because x is the intermediate. Y is the true output. So we label, this is the y. Okay, let's really think about this for a second. What is the logic in English here? We see that, okay, both are 0, we see the 1. We see one of them are 0, then we get the 1, and if both of them are on, we get a 0. So what is this saying? I could see some sort of OR logic in here. If A or B are 0, right? If A or B are 0, then we get the output as 1. So I know there's some sort of OR logic related to the NAND. Okay, so what I'm going to do is just draw the OR, and we're going to try to relate this to the NAND. So we have the output, right? What happens if I literally flip all these bits? The A bits and the B bits, I flip them all. Okay? So that means I'm putting an inverter here. What these inverters do, instead of looking for a 1, they think of zeros as 1s, and they think of 1s as zeros. Right? So this is an OR gate that's looking for zeros instead of 1s. So these two are equivalent. So I'm putting the 3 lines as the equivalent symbol. This is a NAND gate. This is the same thing. It has OR logic within it, but it's OR logic that's looking for zeros. Okay? Now let's try the same thing with the OR gate. So let's take a regular OR gate. Think of it as OR, like literally OR. A or B could be 1, and the output's going to be a 1. So let me just draw the truth table. Wait. 1 second. We label this point as X, and we give it a NOT gate. And we label this point as Y. Okay, then we just draw the truth table really quickly. We have A, we have B, we have X. Let me just draw, oh my god. I should just take my time, not try to rush anything. Because this stuff is really fundamental for what's to come in the other videos. So let's draw all the combinations of the taps that we could switch. We could like this. And we know that OR logic just tells us, okay, we know that there's no ORs here, or, okay, this is OR. That's for point X. Now we flip that because we have the NOT gate. So we don't even need to think about it, it's just the opposite. Okay, now let's think of this in human language. Okay? Let's see the pattern. We know that they're all going to be off in all the other states except for the first state. And I could see some AND logic in here. I could see AND logic. Because A and B need to be a 0, then the output will be a 1. So I know that there's some sort of AND logic in here. So let's draw the AND gate. We have the output Y. But look, what if I add inverters to represent that I'm looking for a 0? These inverters are going to be looking for a 0. So this gate, we call it a NOR gate, not OR. So the NOR gate is just telling us that we want to use AND logic, but we're inverting the input. So we're looking for, if both inputs are 0, then it's a 1. Now let me just summarize this really quickly in a very simple way. So we remember the NAND gate. This is equivalent to an OR gate. And we put the inverters, we just represent like this for short, just put the circles as inverters, as an OR gate with inverted inputs. Okay, now let's draw the NOR gate. The NOR gate is equivalent to an AND gate with inverted inputs. Now you can see that we have an OR type of logic on this side, so these two, we have OR type of logic on this side and this side. So just think of NAND as the opposite, like the OR version of inverting the inputs. And the NOR is just the AND version of inverting the inputs. Now, this is given a name, and this is De Morgan's theorem. And De Morgan's theorem is really, really useful. So don't just forget about this. This is very, very important. Okay, now there's 2 more gates I need to say. 2 more gates, and that's all. And that's how computers are made. just with these two more gates, and there's one more called the buffer, and I think I'll just go through that. But the next gate is called the XOR. The XOR the X just represents exclusive. Okay, so let's just draw the symbol. So it's just it looks like an OR gate but with an extra fin. Okay, and you could think of this in English, exclusively OR. So it's gonna be related to the OR gate, but it's gonna somehow have exclusiveness in here, like VIP exclusive. So let's just draw the truth table. We label this guy as X, A, B. Let's put the 0, the 0, 1, the 1, 0, the 1, 1. These are all the combinations of the taps you could flip. Okay, exclusively OR. So I'm just gonna put this down. Okay, the OR gate makes this one a 1. That's the only difference between the XOR and the regular OR. But this is the XOR exclusively, so only if A or B exclusively one of them are 1, output will be 1. Okay. Now, this goes on with the pattern that I was showing before. We have inverted versions of all the gates, so the only natural thing to think about next is the XNOR. It's literally, you could guess it, the opposite version of what I just explained, the XOR. It's the opposite version, and you could guess how you could draw it. You just draw XOR and you put a circle, right? And all it is the opposite version of XOR. So let's draw the truth table. Okay, so it's not going to be exclusive. So this is just saying if both the inputs are the same, that's it. If both the inputs are the same, output will be same. So 0 and 0, they're the same, so we get a 1. These are different. A and B are different in this one. So you get a 0. They're different again. But look, they're the same now. This is called the XNOR gate. Okay, so now you know about the 7 logic gates. Okay, so this is good. You know about the 7 logic gates? Don't even think about them in Boolean. Think about them in human language. We have AND, literally AND. We have OR, literally OR. And then you flip them. So you get the NAND and the NOR. Okay, then you get exclusively OR. Literally exclusively OR. It's literally in the name. And then you get the XNOR. And you get the NOT gate. Okay? Now let me just introduce you to something called a buffer. It looks just like a NOT gate. And some people, they're like, yo, what's the point of even having a buffer in the first place? Because remember, if there's a circle here, this would just be a NOT gate. But this one, there's no circle. So you could kind of guess what this one's going to do. It's literally going to do nothing. So you have a 0 here, and a 1 here, and a 0 here, and a 1 here. What is the point of this? Why would you... Isn't this just... What's the difference between having this buffer and just a line that does it? You don't even need to put the triangle. Let me tell you. This is just for boosting signals, making them stronger over long distances, like relatively long distances. You just use these to boost your signal. Okay? Now, there's also one more thing I should explain that's really important. And by the way, the one I just explained is called a buffer. There's no like cool name, it's just a buffer. Okay, there's also one more that's really important. Okay, so we have A, we call this one the control, so I'm going to give it C, and we have X. And let's draw the truth table for this one. It's literally a buffer, but it has an extra control, so let's draw the truth table. A, we have C, and we have X. Okay, these are two inputs, so I'm just telling you right now, C is an input, and A is an input, and X is an output. Okay, so let's draw the combinations. Let's just draw out the combinations. Okay. Now, I'm only going to go for this combination here first, and I'm going to go for the second combination and the fourth combination first, where the control line is a 1. Okay, this is just a regular buffer. This just acts as a regular buffer. Alright, so ignore the whole C column right now. If C is a 1, we're only looking at 2 and 4, so C is always 1 in those two rows, I guess. Okay? So the 0 from the A gets transferred to the X. The 1 from the A gets transferred to the X. Now, this is where the cool thing happens. We have a 0 here in the control, and we have a 0 here in the control. And I'm just going to put a dash. Because literally what this does is it acts as a full disconnection from X. So when this is a 0, the equivalent to what I just drew is a wire, a literal disconnect, and then a wire. This is like, I believe it's called a high impedance state. I'm not like 100% sure. So if I'm wrong, just someone comment that and just fix that. But this is how I think of it as. It literally disconnects it when the control bit is a 0. And this is really important because remember how I said we could represent numbers on literally individual lines of wire, right? And what if I have some component, let's just say there's a component and it puts a number onto the bus. But what if there's another component and puts a number onto the bus? Only one piece of information could be on these wires at a time. If two different blocks are trying to put information onto this bus, you're gonna have a bad day. But